So welcome everybody to the Space Awareness webinar, Cassini's Mission to Saturn. My name is Marina Jimenez. I work at European Schoolnet and I will be moderating this session today. Our presenter for this session is Dr. Nick Sergis, a researcher at the Office of Space Research and Technology of the Academy of Athens since 2006 and a member of the Cassini MIMI scientific team. Today we will try to follow Cassini's 17-year adventure and focus on the ways it advanced our knowledge regarding our solar system and how it introduced new multi-level challenges in the field of space awareness. The presentation will last about 45 minutes, and after that we'll have 15 minutes to answer all of your questions. In case you encounter any technical problems during the presentation, please write to my colleague Adina in the chat and she will support you through it. You can find the chat tab on the right side of the screen. I remind you all to close your microphones and your cameras, please. As I said, at the end of the session, we will have some time to address questions to our presenters, so please share your questions, comments, and suggestions in the chat. To share with everybody, please select the option Everyone in the recipient menu. And now I can leave the floor to Nick. Nick, if you're here, you can already start sharing your screen. And for the rest, I just hope you enjoy and welcome to the webinar.
Good afternoon, everybody. I will be trying to share my screen to get us going. So if I have done everything correctly, now you will be able to see both me and my screen. Thank you for being here this afternoon. My name is Nick Sergis, and I'll try to take you through a beautiful voyage through the planets, and basically through one of the most beautiful planets, Saturn. I am a physicist, and I did my master and PhD in space physics. And actually, my master and PhD was on Mars, quite a different planet from what we will be talking today. And I worked in Athens, here in beautiful Greece, and I was inspired to follow that professional path by Carl Sagan and the Cosmos documentary. Hope you have been able to enjoy that. What I currently do is that I'm a member of the Cassini scientific team since 2006, and more specifically, I'm a member of the magnetospheric imaging instrument called MIMI. I work at the Academy of Athens, and I'm adjunct researcher at the Observatory of Athens, although our research is funded from the Johns Hopkins University Applied Physics Laboratory in the United States. My research focuses on the magnetosphere of Saturn, its plasma, magnetic field, and in particular the ring current of Saturn. But today I will be trying to be more general and give you some of the aspects of my research that usually students find more attractive, more appealing. So this is our solar system. On the upper panel, you can see all the planets scaled by their size, so you can really tell how large Jupiter and Saturn are compared to our little Earth and the other planets. And on the lower panel, you have all the planets aligned, but this time they are scaled to their distance from the Sun, so you can actually see how the inner planets separate themselves from the outer planets. And this is a good way to start our discussion about scales, because what students of all ages usually have a difficulty of understanding is how large things are, how distant some objects are, and they are usually trying to use their own experience from everyday life to figure out what far away means or what big is. and they usually fail to do that because our everyday life doesn't offer us that opportunity. Let me tell you what I mean. Um, we will focus on the Saturnian system, as I told you before, which is a system of its own, because Saturn has actually 62 satellites. Seven or eight of them were discovered recently by Cassini. And Saturn is a very interesting planet. It has a radius that is about 10 times larger than the radius of Earth. Here you can see a picture of Saturn with the Earth scaled, so you can figure out what the difference in sizes are. But what is more interesting about Saturn is that its density is quite low. It's a gas giant, so its density is lower than 0.7 grams per cubic centimeter, which means that if you could find a quantity of water large enough, an ocean large enough to fit Saturn in there, Saturn would float. Back to the scale issue. Imagine that Saturn is a basketball, which is easy to do. Then Earth would be the size of a little cherry. And the distance between this basketball and this cherry would be about 3,200 meters. On average, of course, because, this distance changes with the phase of the motion of these two objects around the sun. And the best way to make these more easy to absorb for a student, if you're a teacher and you have students of different ages, would be to give them a map of your hometown. I used a map of London. It's not my hometown, but I figured that there's a good chance that several of you have been at least once in London. So let's suppose that Saturn or Earth, doesn't really matter, is where Big Ben is. Then the other object would be circling in a radius that would cover that distance. So what we're saying here is that if you have this basketball at Big Ben, then your cherry would be farther from where Tower Bridge is, for instance. And if you use that with a map that is familiar to students or children, then they will be able to understand how far this place is really. Let us move on to check Cassini, which is the spacecraft that gave us all that information that we will be discussing today. Cassini is one of the largest spacecraft that humankind have ever sent away from Earth. Actually, is the second largest. The largest, I think, it was the Phobos spacecraft that the Soviets have sent to Mars. It carries 12 scientific experiments, and these three that are highlighted there are the instruments that my team is working with. And here is a very short summary of what Cassini has achieved during the 12 years that this spacecraft has spent in Saturn. Actually, it's 13 years this year. Cassini was started orbiting Saturn in July 2004, and it will end its mission in September of this year. So we will see more about that as we go, but here is a short summary of the amazing things that Cassini have achieved. Let's start with the long journey that had to start from this little cherry, as we discussed, and go all the way over 3 kilometers to the basketball. It's not easy to send something that big that far. So it took 7 years and a lot of effort to get Cassini to Saturn. The travel started on October 15, 1997, and ended, as I told you, in July 1st, 2004. But Cassini did not go straight to Saturn. Started from Earth, as you can see in the green line, and instead of going outwards, it started going inwards towards Venus. Passed from Venus once, then twice, and each time Cassini was passing from Venus, it actually started falling to Venus, only that at the last minute the spacecraft didn't fall, it just gained that boost that needed to raise its velocity so it can get out of Venus's gravity with higher velocity than before. And it did that twice with Venus, and that went through the orbit of Earth and fly by Earth. So it passed through our planet on August 1999, and then it took some extra momentum, gained some momentum enough to get Cassini to Jupiter. And Cassini arrived at Jupiter in December 2000 and started falling towards Jupiter, only that didn't fall at the last minute, escaped the gravity field of Jupiter with enough momentum to get the spacecraft finally 3.5 years later to Saturn. This is the easiest way to get to a planet that is that far away, especially when you deal with a spacecraft that is heavy and you don't have the luxury of using any kind of fuel, and of course you don't have the luxury of using any kind of solar panels at these distances from the sun. Of course, Cassini has 2 rockets and has indeed fuel to activate these rockets, and these rockets have been constantly activated every time that Cassini wanted to maneuver and change the orbit and perform some maneuvers that will allow it to go through certain satellites of Saturn, as we will see in a little while. Well, one of the most interesting and appealing things about Saturn is the Saturnian rings, and there are tons of things that you can easily find yourself from just a quick search on the internet. And I'm not here to tell you about these things. I'm here to focus on a couple of other things that you may find fascinating. For instance, did you know that the rings of Saturn is one of the thinnest structures that we can see in our universe? The rings of Saturn have a thickness that is about from 500 to up to 1,000 meters thick. And as we will see further down, these rings cover a huge surface. If you scale that to our everyday world, it would be like having an ordinary piece of paper covering the a whole football field. So you can imagine how thin this structure would look like, having an ordinary piece of paper in the size of a football field. However, let us concentrate on the origin of the rings. Currently, there are two scenarios about the origin of the rings. One claims that there was once a Saturnian moon, like the other 62, that at some point were blown apart either due to an external object that crashed on a collision, or due to the extreme tidal forces as the orbit of this object got closer to the planet. And what you see as the ring structure today is the little pieces that remain from that original satellite. The other scenario says that it's just material left from the initial nebula that formed the planet, and this material is trapped in orbit and was never able to form another satellite. I have to admit that scenario one is what most scientists favor these days, and that has a very interesting implication. So if we accept that scenario number one is the most probable, then we come to the conclusion that the rings is not a permanent structure in Saturn, and that we as humans are somehow lucky that this feature is there in Saturn during our lifetimes as a civilization. So if in that case, Saturn didn't have rings, and Saturn will not have these rings for long. It just have these rings long enough for us to observe and call this planet Lord of the Rings, please. And here are some images that can show the fine structure of these rings. And although these rings are named, as you probably know, what you may have not observed is that there is a very, very fine structure. And what about the size of the rings? And here is the question of scale again. This is a map of Europe. Most of us are here from Europe. So what I'm going to do now is that I'll let some slice of the rings pass underneath, so you can, in scale, so you can tell yourself how large the structures and the fine structure of the Saturnian rings really is. So what you see here is in scale. Each time you see a gap, like the Colombo gap or the Maxwell gap, or any sort of gap, you can really tell how large it is. You can even fit half your country in there. And I find that a very useful slide to show to students. They love it. Let me tell you now about properties that we can compute from a distance. And those of you that are amateur astronomers or professional astronomers know that even better than I do, because astronomers are the people that usually take the faint light from a star and they can extract a ton of information from that. So what you see here is an example of how imaging of the rings can really tell you the distribution of the temperature in the rings. So you can have dark regions that correspond to higher absorption, which means that they must have higher temperature because they absorb more of the faint light at the distance of Saturn. By the way, the Sun shines 100 times less at the distance of Saturn compared to Earth. And of course, you have bright regions, which means that they strongly reflect the light, and of course, they correspond to slightly lower temperature. And I have so many things to cover, so I have to really go a bit fast. I'll now go to Enceladus, which is a small moon of Saturn, but it's a very important one. It's this little guy over here, and you wouldn't notice normally. And people before Cassini went to Saturn didn't really pay any attention to Enceladus. But again, it was the remote measurements that revealed that something is different about Enceladus. It's the remote observations. This is a small satellite. It's a nice ball, essentially not much, not low, smaller even from the United Kingdom, as you can see, 500 kilometers in diameter. However, when Cassini was flying in some distance from Enceladus, it was the magnetometer that discovered that something is wrong there. And what the magnetometer of Cassini was observing is that this little obstacle in the magnetic field did not deform the magnetic field as we would expect for an object that is a sphere, symmetrical sphere, and instead of getting the expected deformation of the field, we would get something like that you see in the picture, something that was elongated and seemed that doesn't have a symmetry. And that was the reason, a good reason for the scientific team of Cassini to change the orbit. The way I told you before, they deactivated the rockets and they redesigned some of the orbits so that Cassini would pass really close from Enceladus. And then they discovered that there is something else going, something else being rather peculiar about this satellite. On the left, you can see the predicted distribution of the surface temperature in Enceladus, and to the right, you can see the actual observed temperature. And you can see that there is a very strong difference at the south pole of this object. It seems to you seem to have quite high temperatures that are not expected to be there. And in the next flyby, the CIRS team, which is the infrared camera of Cassini, was able to photograph from a close distance and map the south pole of Enceladus. And what this photograph shows, and what this camera does, is that it can tell you where it's cool and where it's hot. It actually can map the temperature on the surface that is being photographed. And what you see here in yellow and red is parts of the surface that have higher temperature than the surrounding. And what you see there is that they are these structures that were called tiger stripes, from where water vapor were ejected in the form of jets that we often see, geysers that we see in Earth, especially in Iceland and in other places. And you had there something that was never expected. Water vapor jets that eject water vapors at a rate of almost 200 kilos per second, and they eject that to long distances because Enceladus has a very low gravity field. So what goes up don't necessarily come down. Best way to photograph the south pole of Enceladus, don't get confused here. The south pole is what you see to the lower left corner. The best way to photograph that is during a solar eclipse. So here Enceladus is in front of the sun, and that makes it easier for us to see and map the whole structure of these water vapors that go out from the South Pole. The explanation that has been given so far is that there must be water beneath the iced surface, and that water is kept in a liquid phase due to the heat that is extracted from tectonic activity, from friction that is triggered due to tidal forces between Enceladus and Saturn. So as Enceladus goes around Saturn, the Saturnian gravity field and the small changes due to the orbit create these tidal forces, which are enough to produce heat to keep the water beneath the ice surface, keep this water warm. And when this water finds its way on to the surface, it is ejected as a jet. Very interesting, especially if you think of what the requirements is to have life in a place in the universe. And what you need to have life is energy, which you have here, water, which you also have, and what you also have here is some salts that appear to be diluted in the water, in the liquid water that is beneath the ice surface. So together with Europa, which is a satellite of Jupiter's, Enceladus is one of the best candidates to host or have hosted in the past life. There were other ways for us to observe these jets from Enceladus, and one way was to wait until or to target the Cassini camera in a way that will capture a star passing behind these jets. That means that when this star was passing behind the jets, the light we get from the star would get absorbed by the weather vapors, and through spectroscopy we could tell what sort of liquid is that causes this absorption. Same here, when you had a specific star passing behind Enceladus through a path that did not intersect the South Pole jets, what you would see in the light that comes to you from the star is a sudden drop, very absorbed drop, like when you see something and then that something is hidden behind the wall. In the case that you had a star passing through behind Enceladus, but through the jets, then you would see a progressive drop in the light while the star is covered behind the jets, and then the sudden drop when the star is behind the obstacle itself. Let me now go to aurora. I don't know if any of you have seen aurora. All of us have seen videos of aurora here in Earth. Saturn has its own aurora, and it's beautiful. And this is a picture taken from Hubble Space Telescope, and it's not a real colored picture. It has been modified so that the aurora would be able to be visible, because the Saturnian aurora has its main emission in the UV ultraviolet part of the spectrum. And well, for us scientists, the aurora of a planet, including the is a very valuable tool. Here you can see a video of the Saturnian aurora, and you can see that it's dynamic. It rotates as the planet rotates, and it can be enhanced, can be stronger at some phases and weaker at other phases. And this is another video that is more artistic. But what we usually do with the aurora is that it's for us it's a way to understand the interaction of the planet, and especially the planet's magnetic field, with the solar wind. In order to explain that to a non-specialized audience, like in your students, you could start by saying how the aurora is formed. And you can see here a nice slide that explains how the aurora is formed. It's formed by solar particles that manage to get through the polar caps inside the magnetosphere of the Earth or any given planet and interact with the upper atmosphere. There, these electron and ions that come through the magnetic field lines interact with the molecules and atoms of the upper atmosphere, and these atoms and molecules are excited. That means that they absorb some energy from the electrons that are hitting them, and they get to an excited state, and then they come right back relaxing from that excited state, and when they relax, they get rid of the energy that they had just absorbed by sending a beam of light. And that happens really fast. That's why any aurora is very dynamic, and what you see from a distance is these night lights. That is the emission of these previously excited molecules and atoms that have just relaxed and emitted the energy that were previously given to them. In our case, in Saturn, you have a complex aurora, and what we do with the aurora is not just to observe, but we use aurora to reveal dynamic changes in the magnetosphere, because every time that there is an enhancement, there's stronger solar wind hitting Earth, Jupiter, Saturn, then this excite state that I described before, which causes the aurora, is enhanced. So what you really see is that the aurora is stronger, is brighter, and also is visible in lower latitudes. The aurora in every planet is usually visible in very high latitudes. That's why You don't see the aurora in the Mediterranean. You have to go to the Scandinavian countries or Canada to watch the aurora. In cases of intense solar wind, this can change. And if you are able to observe the aurora, you can actually tell what happens in a place where you are not observing at the same time, which is very important in the case of planetary exploration, because in other planets you usually have one spacecraft. It's not, we don't have the luxury that we have in Earth, having a whole fleet of spacecraft around our planet. In Saturn, you only have Cassini, and the question that we always have is, if we see a change, is this a temporal or a spatial phenomenon? Imagine you're driving your car and it suddenly starts to rain. Did this happen because you just moved to another place and you changed your location? Or did this happen because it has started to rain everywhere in the whole place? So is this because of your dislocation, or is it because of a temporal effect that just started everywhere? You cannot really tell that unless you have another observation point, unless you have a friend you can call back where you started and call him and ask him if it rains back home, and then you can tell if the whole place is under the rain or it is just that you moved. We have found a way to help ourselves with that problem, and it's called the ENA imaging. And we usually refer to that as our ability to see the invisible. So you have this physical process that is called the charge exchange process, and you have a cool, slow atom, neutral, that interacts with a very fast, very hot, as we say, ion. Ion is charged, the neutral is neutral, and what really happens is that an electron goes from the neutral to the ion. So the ion is neutralized and the neutral now is ionized. So it's just an electron that goes from one ship to the other. What does that mean? That means that you now have a very low energy ion, because now it lost one electron. It was what was previously a slow neutral atom, now lost one electron, and it's a low energy ion, but your hot ion is not an ion anymore. It's a neutral. And it's still very fast. It's still very hot. The only thing is that it doesn't have to go where the magnetic field tells it to go. If you are an ion, you are bound to follow the magnetic field. If you get neutralized, then you don't care about the magnetic field and you can go any place you want, and actually you will go wherever your trajectory was at the minute that you got neutralized. So what we do is that we have this camera, specialized camera, that gets all these energetic neutral atoms that really work like photons, and you can create these nice images of distribution like the ring current of Saturn, which are invisible to the naked eye, but are very important for us. And here you can see what you can get from a remote observation from just one spacecraft. And this is very important because you can use high latitude orbits when the spacecraft is far from the planet and looks down to the planet, and you can see the whole structure, and it's like you have a drone over your car, and now you can tell if the rain is all over the place or if the rain follows your car. Come to the example that I used before. Finally, I will take you to Titan. Titan is the largest, by far, satellite of Saturn. It's a very big object. It's larger than Mercury itself, and still it's a satellite, and it's a very cloudy satellite. Same way as Earth has its atmosphere, but it's rare to see clouds everywhere in Earth. This is a typical picture of the terrestrial atmosphere. You have the same stuff, the same atmospheric circulation in Titan, only that here you have a much denser atmosphere. It's always cloudy, and it's methane instead of water. Cassini ejected a little capsule called Huygens that was landed in Titan on 2005 and got us all these nice pictures that I'm about to show you in a little while. Here there is a simulation video of how Huygens was inserted in the atmosphere of Titan. It's very thick and never goes away, never clears, and you have to go below 50 or 60 kilometers to start looking at some features in the surface. Titan has a surface that is solid. It's not a giant object. It's not a gas object, and it has very, very low temperature methane. Now, what is very interesting is that you can see structures that remind you of Earth. These are a few centimeters rocks, but they're not actually rocks. These are methane ice cubes. This is frozen methane, and you have a footprint on the moon for a comparison of the scale of these photographs. These are a few centimeter rocks, and the big secret is that the temperature of the surface of Titan is ideal for methane to be present in all three different phases, as a gas, as a liquid, and as a solid, same as water is on Earth. So that is why you have a methane circle, atmospheric circle, and chemical circle, same as you have on Earth. And we were able to observe with Cassini these methane lakes. And you can see here again, remember to have everything in scale, otherwise people, your audience will never understand how large this structure are. So you have on the left a methane lake in Titan. I have on the middle the Superior Lake of, this is the second largest lake on Earth in the border of USA and Canada. And I have my own country, Greece, for comparison. And you can put your own country and tell people, this is how big these lakes are. Of course, they are not that deep. But again, remember that Titan is not as large as Earth. Titan's surface is 6 times smaller than Earth. So if you have such a big lake in Titan, it's not really appropriate to call it a lake. It's like a sea. But that's something you can handle. Now, this is an overview, nice overview you can find online of the Cassini orbits throughout the 13 years of its um, mission. And it's really impressive, and you can see how many different places of this system Cassini has covered. It's time that Cassini had to change its trajectory in order to save some fuel. Would They would design the trajectory to pass through Titan and do pretty much the same gravity assist process that we described for Cassini's travel when it was passing through Venus, Earth, Jupiter, etc. Now we did it. We were doing it that for changing the trajectory. We would pass Cassini through Titan, and then Titan would eject Cassini to higher latitudes or keep it to equatorial surfaces. Now, the Cassini mission approaches its end, and these are two groups of orbits that are currently underway. The white one that is not moving has already been completed, and Cassini passed through the outer edge of the rings. Now, what Cassini does these days is that it's trying to complete, I think, 22 or 23 orbits that go between the inner part, the inner edge of the rings, and the planet itself through that small gap. And there is an amount of risk each time you do that because there is a chance that you will crash. But so far, Cassini has completed, I think, 6 or 7 of these orbits that are seen in blue and has not crashed yet. How will this look from above? This is what Cassini does right now. It goes through the gap and down, and then far away from the planet, you can see the sun on the far behind, and again go down and up. And on September 15th, Cassini will fall in Saturn, will return every possible measurement it can return as it will be falling towards the planet. And that was a decision made by the scientific team in order to protect the other satellites. In case you're wondering, why don't we land Cassini somewhere? We cannot land Cassini. Why don't we leave it there until its fuel and its battery is out? We cannot risk that. If you leave Cassini there, eventually due to frictions, it will crash either on a satellite or in Saturn itself. And you don't want Cassini to crash on a satellite, especially if it's one of the satellites that are candidates for hosting life or having hosted life. So you want to preserve that environment for future missions to discover. This concludes my presentation. I have my contact info for you to send me any questions if we don't have time to discuss now. I have put there some useful links for you to check, and I want to thank you all for spending this afternoon with me, and in particular the team that made this possible. The girls that are helping with this webinar: Eleftheria, Adina, Marina, Evita, and Theodora. So I'll return now to, I will exit my I will exit the presentation mode.
For the webinar. It was super interesting. While you change screens, I think maybe I can already start asking you because we collected some questions throughout the chat. If you can actually, first of all, if you can press the button that says start sharing, maybe we can see your face because the camera was not working. Oh, it's okay.
Yeah, sorry.
It's okay, it's no problem.
Start sharing. Yeah.
So regarding the questions, I'll start with, let's say, with Eve Tricarico. She has a question about the Saturn rings. She says, are the rings moving around the planet in a separate motion?
Um, no, the rings actually follow the planet in its motion, which lasts for 10 hours. But there are some differences because the rings themselves consist from objects of different size. What you find in the rings can vary from the size of sugar grain, so dust, to the size of a small car. So not all of them travel with the exact same velocity, but in general, the rings rotate around the planet same way the planet rotates around itself. 10 hours, 48
Okay.
minutes.
So I guess that answers my first question. The second one is from Anaeli, and she asks, is there any explanation about the gaps? Why are they at those places when you were talking about the gaps?
Well, the rings of Saturn are really very dynamic, so there are changes that happen all the time. The gaps, it's something that is not really solved in detail. In detail, there are dynamic equations that would tell you what is the proper orbit, the expected orbit for each particular size, each particular mass of an object that is around Saturn. However, what happens sometimes that there are collisions between these particles and these small grain objects that form the rings. But the main gaps are expected to have formed from satellites that were at that orbit, and at some point they were dissolved, they blew apart, and they left a small path free from particles. And so far, particles and other objects have not been able to fill that empty space. So it's like at some point something went around, swept a small corridor, and ever since this corridor is empty. It's been filling, but very slowly.
Okay, thank you very much. There's another question. This one, it's also about the rings. Eve is asking again, why are the rings so thin, and if there's an explanation for that?
Yes, there is a better explanation about that. It's the centrifugal field that makes these rings be so thin. So Saturn is a fast rotate. Is a fast rotator. Saturn and the rings rotate, as I said before. They make a full circle in a little less than 11 hours. So they rotate more than twice the speed of Earth. Now, if you imagine the size of Saturn itself, and imagine that the rings are farther out, then these rings rotate very, very fast. So it's like spinning a pizza very, 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 very fast. It's the same way that you use to make a pizza very thin. And imagine that happening for ages. And you will end up with something that is very thin.
Okay, I really like the pizza comparison. There's another question also related to the rings. Ali Murad is asking why these rings don't exist on another planet.
Well, they do. It's not. Saturn has the most impressive rings, the most spectacular rings, but there are other planets that also have rings, and Jupiter has rings, and Uranus or Neptune, one of the two or both of them have faint rings, and it's not. It's the same process. It's either some material that was left from the formation of the planet, or some small satellite that has blown apart due to collisions or tidal forces. And but the rings that Jupiter or Neptune have are very faint, and it's not their main characteristic. But if you look it up, you will find out that there are other planets that have
Okay, good
rings.
to know. And then there's another one last question about also about the rings from Narcisa. She says, are the rings rotating to Saturn separately?
Could you repeat
Rotating
that? Are the
separately.
rings? Uh, no, as we said before, the rings rotate all together with very small differences. Very small differences, because each individual part in the rings does not have a purely azimuthal, as we say, velocity. They sometimes go a little farther out, a little farther in. They collide sometimes with themselves. It all depends on the size. Now you have to have in mind this, that the material that the rings are made of is basically ice, water ice, and dusty water ice, dust and ice. And you know what that means? That means that each individual object within the rings, as they rotate, it changes its mass because of the friction, because of collisions, because of the faint light that hits this small part of ice and changes its and melts a little bit of that part. So you have some dynamical changes. So you have something that starts at the size of a basketball, and within some years or hundreds of years, which is nothing in terms of solar system age, it can turn out to be a volleyball, and later on a tennis ball, and a ping pong ball. And you can imagine that the expected trajectory, it's a little bit different for each size.
Okay, we do have one last question from Anaeli, and this one is, what is the origin of the magnetic field in Saturn?
The origin of the magnetic field, not only in Saturn, but in every planet that has an internal magnetic field, has to do with its core. Um, the origin is the rotation, and especially the rotation of the core. So in order to create a magnetic field in a planet, you have to have first a solid core, and Saturn, Jupiter, Earth have a solid core, and apart from that solid core in the center of the planet, you have to have a conductive solid core. The core has to be conductive, which is something that usually happens because this core is made of iron and silicon, which are conductive material. And then if you have a rotating planet, and especially if you have a fast rotating planet, then the rotating core can create some, because it's conductive, can create electric currents, and electric currents are the source of the magnetic field that you see on the surface. In order to have a magnetic field in physics, you need to have a current. And this current is created by a solid conductive core plus fast rotation. If you lose one of the two, then the magnetic field will end, will cease. And this is what happened in Mars at some point. Mars has a solid core. It has a rotation, but it was the conductivity of the core that changed, actually the amount of iron compared to silicon that changed and made this magnetic field go away. Venus has a solid core and could have a magnetic field, but it rotates very, very, very slow. It takes over 243 days, if I remember correctly, for Venus to rotate once around itself. Now, Saturn and Jupiter are fast rotators, solid, core, and conductive. There you go.
Okay, we have two last questions from Enio and Sergio, and for the participants, I think maybe we'll have to end with those two. The first one from Enio, he says, pieces of matter go out from the ring to the space, if they do go out from the ring to space. Yeah, sorry, I was not very clear.
Could
He's
you
asking
repeat?
if any pieces of matter go out from the rings to the space.
Mm-hmm. Well, small, the smallest parts can sometimes make it out of the system, of the ring, but they have to be very, very small, at the size of smaller than a dust grain, and they have to be hit from another object, from another particle, in such a way that their velocity will be radial and they can get out of the system. This is something that happens very rarely. These particles have a very high velocity, moving azimuthally, going around and around, and it's very hard for them to go out of the system, so they are trapped there. There is a much better chance that some of these can fall into the planet rather than going outwards.
Okay, and we're getting to the last question from Sergio, which Adina here was also asking the same question. So Sergio asks, Cassini will crash into Saturn, but Saturn is not very dense. Will it be totally destroyed?
Yes. Now, what you see when you see Saturn and you see this round sphere, and you know, I told you that it's a gas giant. What we call a surface in such a gas giant as Saturn or Jupiter is the limit where you have a pressure, gas pressure that equals the atmospheric pressure, 1 atmosphere. And when you go farther down, the lower you go, the higher the pressure would be. So eventually, the high pressure will crush Cassini. We won't be able to tell what happened. We will just see a black screen at some point. And we will know that at this certain point, the transmission system was destroyed. But that doesn't necessarily mean that the spacecraft itself was crashed. But you expect that a few seconds later, the pressure would be so high. It's like having a little submarine sinking in a very, very deep ocean in Earth. So if you start sinking a submarine, then at some point you will lose transmission. You will see a black screen, and then you know that it has started to crash, and you will know that eventually it will crash. So that's what will happen to Cassini.
Okay, so now we know. So thank you very much, Nick, for all of your answers and for the presentation. It was very interesting and very clear. For all the attendees, just to remind you that the recording of this webinar will be available in the following days. So please follow the career hub of the project to access the resources later on this week. And well, I think that's gonna be it for today. So again, thank you very much for your time, and to everyone, see you next time on the next Space Awareness webinar.
I thank you for your afternoon, and again, I'm deeply sorry that I didn't push the damn button about sharing my camera and you couldn't see me. I didn't notice that, and I thought that you were able to see me, but I hope that you were able to see my screen
No
very
problem. We saw the
clearly.
screen, we saw the simulation, so it looked fine. So don't worry about it.